Hand Tremor Sensing Module Group 9. Today we start off by going over specific diseases we plan on diagnosing with our medical device. Some background information on tremors will include the identification of different tremor types as well as the frequency ranges of the most common tremors. We will then move on to describe how to build the tremor sensing module to sense all types of tremors mentioned. We aim to construct a circuit able to develop an actigraph for which our medical device will be used to diagnose our subject for tremors. We will then go ahead and demonstrate how we test the modules with the live subject. And finally, the actigraph should be used in determining rest and activity states, which will aid in diagnosing disorders for which tremors are primarily a symptom. For starters, a tremor is an involuntary shaking of the body. Tremor is an unintentional, rhythmic muscle movement involving to and fro movement of one or more parts of the body. The two main types are physiological and pathological. In some people, tremor is a symptom of a neurological disorder or appears as a side effect of certain drugs. The most common form of a tremor, however, occurs in otherwise largely healthy people. Although tremor is not life-threatening, it can be embarrassing to some people and make it harder to perform daily tasks. This is due to the characteristics of tremors, which may include a rhythmic shaking in the hand, arms, head, legs, or trunk, shaking voice, difficulty writing or drawing, or problems holding and controlling utensils, such as a fork. Some tremors may be triggered by or become exaggerated during times of stress or strong emotion, when the individual is physically exhausted or during certain postures or movements. Tremors may occur at any age, but is most common in middle-aged and older persons. It may be occasional, temporary, or occur intermittently. Tremors also affect men and women equally.
A useful way to understand and describe tremors is to define them according to the following types. Parkinsonian tremor, which are commonly due to brain trauma in which brain structures are compromised, such those as in charge of movement control. Patients for the most part have trouble initiating movement and are generally over the age of 60. Essential tremor, aka benign tremor, are related to genetics and usually affect hand, head, voice, and tongue. Such patients exhibit a repetitive yes head movement. Cerebellar tremor occurs at the end of a purposeful movement and are caused by lesions or damage to cerebellum. These patients have speech problems or rapid eye rolling. Dystonic tremor, for which they have movement disorder where they have involuntary muscle contraction, twitching, or repetitive motions, and for the most part display abnormal, painful postures and positions. Complete rest can help relieve this type of tremor for this patient type. We also have psychogenic tremor, also known as hysterical tremor, usually occurs in patients with a psychiatric disease, can occur at rest or during movement. Distracting a patient can decrease tremor activity. Ruberal tremor, present at rest or depends on the posture, associated with conditions that affect the red nucleus in the midbrain. Orthostatic tremor, muscle contractions that occur in legs and trunks immediately after standing, usually occur when a person stands in one spot. Tremor activity decreases when the patient sits down, and also high-frequency tremor is greater than 12 Hz. And lastly, we have physiological tremor. Occurs in normal individuals with no clinical significance. Usually can be seen with visible eye. Increased emotions, alcohol, drugs, fever, physical exhaustion are caused by increased tremor activity.
In terms of the mechanical interface design for which we wish to create voltage by inducing mechanical stress, in order to properly detect tremors, we will be using a piezoelectric vibration sensor as displayed in the figure to the right. This sensor will be used to measure mechanical waves which are provided by a tremor, and this device works by measuring displacement, which will then translate mechanical waves into electrical waves.
A few factors for us to consider for a proper output. We must acknowledge some interference we will come across. Such interference include different kinds of noise, such as sounds, vibration, and gravity. For this reason, we must implement a specification in order to get an accurate reading. In our design, we will also consider the easy as well as a simple implementation of the device.
The following are specifications we must meet in order to achieve satisfactory results. Input wave of 5 through 15 Hz frequency. Must cut off frequency outside this range. Must amplify input signals. Transfer signal into one readable by LM3914 display driver. Input display must be easily readable by the piezoelectric vibration sensor, where it will yield an accurate output display, seen in the oscilloscope and actigraph.
The following components were implemented in the lab. The transducer with the patient interface apparatus will now be connected to the input terminals. With no displacement of the transducer, we confirm that the DC voltage at the input to the envelope detector is at the ground potential. We also adjust the potentiometer to adjust this voltage to 0. Then the nominal voltage gain values in these laboratory instructions will probably implement a level of sensitivity that is too high. So we simulated a very slight tremor by the patient and measured the voltage on pin 5 while observing the display. Then we reduce the voltage gain by lowering the value of the resistor 2 in the input stage until the display shows only one segment lit. Then we tested the complete system with tremor amplitudes that simulate normal and pathological values. As an option, you can enhance your system by adding a sensitivity switch. The normal screening mode, as per the specifications, will be used to distinguish between normal and Parkinson's subjects. The second mode will be applied to subjects with significant tremors to further classify them as moderate or severe.
Wherefore, we obtain this circuitry displayed on the protoboard. The figure on the right is showing the fine apparatus as it will measure different tremor types. With a long piece to the left of the protoboard, having the piezoelectric vibration sensor attached, will be used to measure the mechanical stress or displacement given off by the tremor for which it is converting to voltage, and essentially an output, which the actigraph will display as an oscillation.
In our demonstration, the transducer consists of a piezoelectric plastic film that responds to the tremor motion of the hand of the subject. Then the input amplifier creates a high-pass frequency response based on the capacitance of the sensor combined with the amplifier's input resistance. The second amplifier has a low-pass response, and it sums the output of the first amplifier stage with a DC offset voltage from a potentiometer. Then it will be adjusted to optimize the DC level of the signal to the LM3914 and 0 the display. Then the envelope detector processes the signal to condition it for the display with a switch to select between the two modes of display. And finally, the piezoelectric vibration sensor will be the interface between the subject and the transducer.
The following are things we noticed throughout our trials. We had to keep subjects as relaxed as possible in order to provide a more accurate electrical signal. To ensure subject relaxation, his or her arm should be relaxed. He or she should be sitting down and must be looking straight forward, since seeing their hand or the sensor light may lead to false readings. If the subject is tense, unnecessary signals may be picked up from frequent movement of the body or voluntary movement of the hand.
In sum, things we took from this project were that clinical diagnosis may be drawn from these measurements. Overall public opinion of tremors is positive. We learned the significance of an actigraph in many aspects of a person's life, such as for tremors specifically. We learned the application the actigraph has, but also how they can help in the improvement of a person's life through diagnostics. Working on the project helped improve our electrical engineering skills. Our problem solving as well as our critical thinking skills were improved as the project progressed in order to get the appropriate reading in the clinical world. And lastly, trial and error is essentially the key to science.